Good morning.
Hey, good morning.
Yeah. So we have few minutes, or should we start now, or we should wait for a few minutes?
Let's wait for a few minutes so we can start at 10:30.
Yeah.
Yeah. Okay, I think we can start.
We'll start. No issues.
Okay, great. So welcome to our day 5 of this course, Introduction to NDE Inverse Problems, Imaging and Data Analysis. So today we will try to talk about the emergent applications and future focus, which will be like a capstone of this course. We have covered the fundamentals of inverse problems for in NDE. We talk about imaging, sensing, and data processing. So we will look at what we have been doing in the field of NDE for the past several decades, especially when we talk about ND 3.0 for the past several decades when we use computers and digitization for the advanced NDE techniques. Then we will try to go over some of the ongoing efforts in the NDE 4.0 when we are talking about Industry 4.0 since 2010 and 2011. Finally, I hope that we can have an open discussion on active research fields, particularly in the data processing and imaging and sensing for ND problems at the end of this course. With that, we will start the overview of today's lecture. So I gave a similar plenary talk this year at ISOM conference. So a lot of materials has been used there, and I think it's a very good occasion to talk about these materials again at the GIAN course. I had a very good experience and I really enjoyed teaching the past 4 days, and I hope the last day will be a time that we can all together and look forward to see what we can do and what needs to be done in this field. So I'll go over a brief history of industry revolution and the relationship between industry revolution and NDE, because definitely NDE is part of the industry revolution. Evaluation and testing is really critical, as I said before, for production, for the advances of materials, and also manufacturing. Then we'll talk about the concept of Industry 4.0. We will briefly touch the impacts of Industry 4.0 to NDE and how the paradigms in NDE 4.0 has changed from the previous NDE techniques we've been working on. Then I will try to use several NDE 4.0 projects at Michigan State to talk about our vision on the advanced and future NDE techniques. And well, hopefully that will open for some discussion when we talk about the trends in industry and NDE 5.0, what we need to do in the next 5 to 10 years. A brief history of the industry revolution. I'm sure everybody is familiar with this. The first industry revolution happened in the late 18th century, and also called Industry 1.0, where you see the mechanical production. The advent of steam engines, transportation technologies. So basically, machines, came out, and you can see the first power loom in 1784 came out in UK. Steam locomotive. This is 1831 picture in the United States. Also, you see the the transportation, particularly for example, this the first iron bridge, because of the advances in manufacturing. So you see the new ways of making those infrastructures during the first industrial revolution. Well, about 100 years later, mass production becomes possible through the second industrial revolution, where the technological revolution, mainly due to the invention of electricity, that led to the major technology advances in manufacturing process. So you also see the chemical, pharmaceutical industries, bloomed, and telegraph and power transmission um, became possible there. So I just list two pictures in the Midwest of the United States, showing you one of the first production lines uh, in Chicago, Illinois. And the second picture shows the workers on the first moving assembly line, where they put together magnetos and flywheels for Ford in Michigan. So Industrial Revolution started about 70 years ago in 1950s. And this is the time we call digital age, where the invention of digital computers, PLC, from programmable logic controllers, becomes possible. And also, that's when the machine learning ideas was introduced in the 1950s in the United States. Computational models are widely used in the third industrial revolution because of the um, computers. And that's when people talk about automated data processing, let the computers to do the work, um, that human laborers are doing, and people are trying to make the industrial process more automated, more efficient, and so on. So you see the increased productivity through this Industry 3.0, and people trying to reduce cost and downtime while increase the reliability. For ND, this means like the integrity, safety, and maintenance of complex systems. Well, associated ND development, you can see, well, there's a lag between Industrial Revolution and NDE, but NDE came out almost, when people realize they need to um, test and make sure their products are in good quality, and also they want to make sure their in-service life is going to be extended as long as possible. So the NDE 4.0, I'm sorry, 1.0 technology are some of them listed here. Usually people do periodic visual inspection, dye penetrant, pad testing. That's the very simple but effective mechanical waves introduced into the material. And a lot of philosophy there is reactive and corrective. Simulation was used there, but based on empirical models. And the data format for 1.0 are text reports. Then ND 2.0 technologies came out, where we have analytical models developed for simulation. And the data format are mainly analog, although there's some mix between text and analog in that era. So you see eddy current, ultrasonics, X-ray, and so on becomes really prevalent. People talk about scheduled inspection, doing corrective, maintenance, and start talking about prevention. So preventive mindset has been introduced during NDE 2.0. When computers becomes more and more, available to the industry, where of course we'll deal with ADC. That's what we mentioned in last lecture when we talk about sensing using digital computers. Computational model has a very big leap where people are now using computers to do those simulation, and you'll see the invention of those numerical techniques. For example, well-known finite difference, finite element, integral equations like a method of moments and so on. And use computers, you can realize the visualization of field to understand the flaw energy or the flaw fields interactions. And you can see the different flux fields. You can see those current fields, for example, for eddy current problems, and mode conversion in UT propagation. The use of digitized data becomes prevalent, and people try to understand the analysis of those data in an automated way. And that's when people realize, the data volume can be very large. While the buzzword later on became big data, of course, big data means a lot more than a large volume data. But in ND 3.0, you'll see those auto analysis programs for data, try to achieve accurate and consistent analysis, eliminate operators fatigue, improve the performance due to the ADA system, while encoding expert knowledge into those digitized approach. Real-time data processing becomes possible, and that's when we talk about data sharing and benchmarking problem. This is actually the age not very far away, and I believe most of us, and I'm not sure about the young audience here, but this actually is what happened in 1970s to 2000. Let me give you a framework that I personally think are the key elements of ND 3.0. You have different type of sensors for ND problem. We covered that in course 1 and also in the first couple of days when we talk about different physics of ND sensing, like eddy current, ultrasonics, magnetic, and so on. In 3.0, we use digital computers, so we get A to D conversion, then use digital computers to process the data. We have advanced data processing techniques. We do data fusion classification through AI and machine learning. As I said, the advanced simulation models are actually a very key theme in the 3.0. The goals of 3.0, you can see we want to visualize the data in different dimensionality. We hope to reconstruct and visualize the defect so we can have a better characterization of the defects. We talk about diagnosis, prognosis, and ultimate quantification, and POD is widely used there. The purpose of doing all this in NDE is multifolded, but I just listed a couple of here. For example, the estimation of RUL, the optimized or condition-based maintenance problems. I list several results here from a project that we collaborate with APRI for the past several decades. And some of data you have seen that in my previous lectures. That's the nuclear power plant steam tube inspection, where we can use eddy current sensors, different type of eddy current probes, to get the data at multi-frequencies. And in ND 3.0, you can use different way to facilitate data collection, and robotics has been used widely in the industry. So you can have those data processing. For example, here I just show you the enhancement of the data using digital filtering in the ND 3.0 era. I just list a few examples of ND 3.0. It's not my intention to go over these 3.0 technologies in detail today. I want to spend more time on the 4.0 discussion. I just want to show you the the advances in this field when we're using, for example, the air pre-auto analysis software and how we apply this in the field trials to save the time and the costs for critical infrastructure maintenance. So this shows you what happened actually in between 2002 and 2007, where you can see the improvement of using auto analysis software. So we save the inspection time or inspection and analysis time from days to hours, while we improve the detectability, um, as you can see from this table. This is another example of ND 3.0 system. This is a successful project that Michigan State working with Boeing and United States Air Force Research Laboratory between 2000 and 2010. I was also a PhD student at the time, where we developed the GMR sensor array. The data collection was facilitated by the robots developed by Boeing. The problem is the crack on the fastener problem. I talked about this problem previously. This is a important problem when we're talking about aircraft safety, especially when we talk about the multi-layer structure. So what I want to show here is just a small part of this big project on the digital data processing, where you can do the data fusion from low frequency and high frequency GMR data and do the fusion. And you can see the results after the data fusion. If we do that, while using advanced data processing techniques, you can really improve the data representation and has a very good correlation with the subsurface defect in terms of its location, sizing, and also depth information, right? So this is a good example of using ND 3.0 technologies to improve the sensing capabilities of a GMR system. Well, this is a a picture where we to show the motivation of advanced technologies to get the robotics involved in the inspection of aircraft. So before that, human operators or inspectors have to climb onto the aircraft body, for example here the airplane wings, to do the data collection. Even you have advanced data technology, advanced ND technologies there. So what we developed in, let me play the video for you. In the ND 3.0 age is, sorry, let me play that, is we can do the edge computing at the sensor end, where you use real-time digital signal processing hardware and software. So you can get the data in real time, do the data processing, for example, here the corrosion from inspection from the magneto-optic imaging, which is a hybrid technique by combining electromagnetic and optical technologies. So you are getting a real-time 2D images from the garnet film sensor, where the magnetic field is in the same direction, or the either axis direction of the magnetic film sensor. So you can get really high sensitivity images, while image processing technique help you to do the real-time noise removal, and also you can also do real-time data classification after the integration of the sensor and also the inspection tool. For example, here is the KUKA robotics. Let me play the video here.
You mean,
Yes.
yeah. In this video that we are seeing, the first video, that is corrosion raw data,
Yes.
the left first one. How do we make out that it has some corrosion?
Yeah, it is a sample with corrosion corrosion damage there. So the corrosion is actually, you can see some of the black donut shape damage there. That's a corrosion site, and it is imaged using the MOI imager. When you can see the moving is due to the moving of the sensor itself.
What are these lines which are being represented here?
So those you're talking about those like spaghetti shape of lines. Is that what you're talking
Yeah.
about? Yeah.
Yeah.
So those are the magnetic domain wall noise coming from the sensor itself. So let me explain the physics of this briefly. So magnetic optic sensor, you have the configuration. Let me use annotation here. So let me draw it here. So you have a light source, which is LED light source. You have the sample here, which is the multi-layer structure. So you have polarized light coming from the light source, and it will be reflected by the surface of the, for example, aircraft body. And you have maybe defects like the cracks or corrosion in the sample. Well, we can have a camera here to pick up the reflected LED light. Well, the polarization of the LED light will not change by simple reflection, but if we add a layer of we call it magnetic film sensor, or this is a magnetic material where the magnetization field is polarized, the light incident and reflected, so the light is passing through this magnetic film twice, where the magnetization is proportional to the local magnetic field. So what we do in this MOI is, I lost my cursor again. I hate this. Come on. I have to do this again. Let me draw this picture and do it again. So I have light source here. I have the incident light, reflected light. I have a optical sensor to get images. Well, if I design the sensor together in a sensor module, where this end I will add a magnetic field, and beneath that we'll add the eddy current excitation. So this is the hybrid technique where we use eddy current excitation to generate the secondary magnetic field, and the secondary magnetic field will be perturbed by the defect and generate normal magnetic field. The normal magnetic field will perturb or change the polarization of the LED light and captured by the sensor here. So what you're seeing here is basically the conversion from the local magnetic field perturbation to the polarized light angle, and that change of the polarization angle will show those dark region in the magnetic field. Well, go back to a question about those spaghetti shape of type noise. Those are the intrinsic magnetic domain wall of the magnetic film sensor. So that's due to the magnetic domains. And one thing you can notice here is it is static in your imaging data. Actually, this is video, right? So the magnetic domain wall is static to the operator. Why is that? Because it's moving along with the sensor, while the defect, here's the corrosion beneath that, is moving because there's a relative motion between the sensor and the structure, right? So that's why you are having this noise here. And there's a thesis in about 2001 or 2002 dedicated to remove those spaghetti type of noise using the motion-based filtering. As the observations, the noise or the domain wall, spaghetti type of noise is moving along with the sensor while the defect signal is not. So you can actually remove that using the sequential images you are getting from the video. Is that clear?
That looks okay.
Okay, yeah.
Yeah.
So let me play this video again so you can actually look at this again. So the domain wall is almost static, right? That's because it's moving with the sensor. And you can also see some type of domain wall here, right? And also the black line here that is the edge of the lap joint. So you can see the edge effect there. Well, those donut shape, you can see some of them look some like a donut perfect circle if you do the edge detection there, and some of them have some additional lobe. That is due to the perturbation of the eddy current in the structure, which will generate the normal magnetic field and captured by the optical magnetic field sensor. Well, we can see the real-time data processing can be done on the sensor end. And let me play this video again. That you have a sensor mounted on the robotic arm, moving on the real aircraft fuselage, and then collect the data real time. It can also be done handheld. That's me actually in 2007, 15 years ago. And this shows you. Let me stop here. This shows you. The left is the raw data when I'm collecting the data. Then the right is the real-time process data. The green bar shows this is a classification results, which means there's no defect. But when a defective signal passing over, then you're going to have a real-time classification. So you can see, I'm sorry, you can see the red bar flashes. So let me play this again. I think this is a very interesting demo. So we went to KUKA Robotics, bring the sensor there. So all the sponsors, all the researchers are there. So we are doing this demo there. Pay attention to the red bar. Yeah, so there's a defect signal. You can see the shape changes. You can also have the beep sound there. Yeah, so that's a very interesting project. And this technology has been commercialized in 2007, I believe, and sold to the company. And the MOI instrument has actually been widely used and adopted by the major airlines in the United States. So this is actually a technology that's been used now in the industry. Any other questions?
I check it once. Any questions from audience side? I don't see anyone in chat right now. If
Okay.
it comes, I'll just update you. Yeah.
Okay, very good. So let's look at this as a summary, what has happened for the past several centuries. Well, the industry 1.0, as we just see here, for ND 1.0 associated with it, that we are dealing with a detection problem when we do the manufacturing. We want to develop a procedure and a standard of make sure our machines are going to operate safely, and most of the time is human inspection. While Industry 2.0 electric power mass production becomes available, then there's a tremendous amount of NDE techniques development there, and analog sensors came out where people start talking about the characterization of defects, the maintenance, and the reliability of the complex system there, starting of the 20th century for NDE 2.0. Well, start of 1970s, we start talking about ND 3.0 also. The industry 3.0 came a few decades before that. And in that, that's the technologies I'm sure most of us are now doing on a daily basis and are very familiar with. For example, detection, monitoring, prediction, and so on. We talk about ADA, we talk about SHM, we talk about data fusion by leveraging the computational advances in the field. Start of 2010, 2011, Europe introduced the concept of Industry 4.0. And that's when we talk about cyber physical systems, cloud computing, 5G communications for the past 11, 12 years. Well, actually, before the concept of Industry 4.0 came out, there's a lot of practice that are actually doing the same thing. And like in the US, where we talk about smart city, smart connected systems, that's actually the same concepts as the Industry 4.0 concepts, right? Then we talk about smart factory here, advanced manufacturing. This is where we are now. We are in the 4.0 state age for Industry 4.0 and the associated NDE 4.0, where we talk about besides what we have been doing for ND 3.0, we are now talking about more like prevention, how to involve action and control in our complex systems, and I'm going to talk about that in detail, and and hopefully to convey that to you, what I mean involved action and control in our NDE. Well, you see the word smart a lot. We'll have smart robot. We'll have smart manufacturing. Digital twins also came out. Although I know this is a fancy word, a buzzword. People now talk a lot. But before that, we do a lot of similar work on. We just didn't call it digital twins 20, 30 years ago. We are now looking at the information fusion and learning and AI-enabled systems. So we are actually working on several projects now at Michigan State, and I'll show you that in the next 30 minutes. Well, so some more discussion on the first industrial revolution. So you see a lot of ideas and concepts being introduced. For example, Internet of Things, smart cities or smarter cities. That's a name called by IBM, where you have a lot of key elements here. I just want to point some of them. So you're going to use the infrastructure of Internet of Things, where you do a lot of distributed sensing, big data collection, and data communication, where you deal with, for example, the mobile devices, edge computing, edge IoT. You have to have a good data centers for storage and processing. So you can have like IoT enabled like transportation, cities, factories, and so on. Where you see for NDE or for people who are doing sensing, the smart distributed sensors becomes prevalent. where wireless are dominantly used nowadays. So people are now doing a lot of data sharing and exchange. Sometimes you notice that, sometimes you don't notice that. And at the sensor side, a lot of data analytics can be done. Think about your smartphone, and the smartphone you have today comparing to the even the smartphones you had like 10 years ago. And before that, we have a smartphone, we have phones with some very limited computing capabilities, right? Before we call smartphone, we still can have a phone taking pictures, doing play some fun games there. But you can see the advances of those hardware and software in the past for the past 20 years. For healthcare problem, I would just mention this because I think this is definitely a promising field where we can see the IoT industry 4.0 can help to revolutionize this industry. People talk about precision medicine, personalized medicine, and diagnosis, telemedicine, AI in healthcare, where you see a lot of wearable devices now are being developed and used. Then you have the advancing device communications, so you can also deal with a lot of data aggregation, pre-processing, storage, and analysis, and so on. One thing to point out is data security. Um, this is very important for healthcare and also for ND people. This is important. Not mentioning that the data sharing, information sharing is important, but there's a lot of safety concerns there, security concerns there. For 4.0 in industry, one comment I want to make here is I don't think this 4.0 industry 4.0 we're dealing with or we are actually experiencing now comparing to the previous three revolutions. Now it is not based on new breakthrough inventions. I don't see breakthrough inventions in this industry 4.0, but we are doing a very good job of integrating things together. So we have innovative use of for example, the IoT infrastructure to leverage existing technologies, which will result in new paradigms in different industrial sectors. Okay, so you'll see the concept of digital transformation, digitalization, for example, digital twins, edge computing becomes popular. Although digital twin is not a new concept, although we mention this now a lot, but 20 years ago, this is nothing but a simulation model and generate a very comprehensive data set digitally. We just didn't call it digital twin at the time. AI machine learning, this has been there for 70 years. But now it has been revived, and people talk about deep learning due to the advances of the both hardware and software. Well, we talk about cloud, storage and computing, blockchain becomes a hot topic several years back, and look at what's been happening on the cryptocurrency out there, right? So we are experiencing some interesting stuff and a new way of doing data communication. But as I said, this is a innovative use of a lot of technologies being out there, but still I don't see new breakthrough as of now. Maybe it'll happen, But at this moment, this is my personal take here, and you don't have to agree with me, but this is my my personal opinion. Well, if we narrow our problems into NDE and asset management, and look at the digital twins more, then the concept of smart assets came in. So you want to have a smart way of managing the assets. So digital twins give you a virtual representation of an asset, or a fleet of assets, or a fleet of fleets. So the key components of digital twins, you're going to have simulation model, you're going to have a what-if simulation for future scenarios, and the last level is the operations optimization, where you can do predictive maintenance, reduce the downtime, and update the asset history. So this picture actually shows you a better way of looking at digital twins based on what I just said in the previous slide. There are three layers there. One is layer number one, doing assets monitoring, where you have sensors network data with edge computing capabilities. So for NDE people, for SHM people, you detect the anomaly at this level. While you do processing of those data, for them a data-driven model, fixed-based model, and so on, you want to do data fusion from historical data, from experts' knowledge, and interact with your data storage and computing facility, for example, cloud computing, database technologies there. After you understand and process the data, the second level of digital twin is you want to have a what-if simulation. So you can see, what will happen in the future by understanding the current state of the assets. The last level, stage or level of digital twin is the optimized assets management through diagnostics, visualization, predictive maintenance, and control, where AI becomes a very important tool when doing those optimization there. I probably can skip some of the slides here. I don't want to distract you too much from what we're going to cover in the NDE course, and NDE 4.0 here. But this is something has been out there and can be a separate, maybe hours-long talk when we talk about the relationship between the Industry 4.0 and the advances of AI or machine learning. While different people have different way of understanding the machine learning and AI relationship. Some literature think machine learning is a subset of AI, while deep learning is a subset of machine learning. Well, some people don't agree with that, which depends on the ways of look at the problems. So sometimes AI is not necessary to involve machine learning. So there are some overlaps there. Well, for NDE, as I mentioned in previous lectures, we've been using artificial neural network starting from 1980s. And actually, Michigan State Professor Woodpark's group, and she's the pioneer of using neural network for NDE problems, particularly for damage characterization and reconstruction in the 1980s and 1990s. And there are some questions you can ask. This is beyond the scope of the course and also beyond my expertise. Is can AI make machines or robots learn to learn? Right. So there's a lot of interesting research directions out there. A showcase of what we have done at Michigan State campus is we involve AI in autonomous driving, and the first electric autonomous bus has been put into service on campus since last year. So this is the bus now running on campus, connecting a few stops and the transport students from a parking lot far away from this, the central part of the campus. And actually, if you have time to visit us, I think this will be a great experience to try it on campus. And other jobs replaced by AI, you can see at least a few them here. You know, I just see this will have a revolution in the industry. But a lot of discussion can be happen here, a lot of debates, and I think these are very very fascinating and interesting topics here. Well, let's come back to NDE, right? That's this course is about. And let's revisit the NDE 3.0. This is what I make changes to that framework, which I introduced years back. But look at 4.0 framework here. I highlight something in red, and you'll see the advances from 3.0 to 4.0. Now we have new ways of doing sensing, and we are taking advantage of edge computing and decision making. We have new ways of doing communication, and data engineering is definitely important here. Then you can better understand data through data analytics at the sensor end, at the data center site. And with the understanding of those data, we're doing like AI, machine learning, deep learning based data processing. We're looking at the fusion of information. Remember I mentioned about the difference between the data fusion and information fusion. I'll elaborate a little bit more when we talk about um, the information in all different aspects of NDE 4.0 very soon. So we see the concept of digital twins there, but one key difference from NDE 3.0 is we'll have a loop where hopefully with all those data we can have a semantic learning concept which help us to do a better job of actuate the sensors, control the system that can help us to do the NDE data acquisition and processing. So I label the smart there so we can do some smart robotic NDE. Well, the ultimate goals are very similar. I just list them here. That we just hope to get better assets management and optimized maintenance and decision making. Now I will list a few projects now going on at Michigan State, and hopefully will give you some idea what we're doing here, and we'll use this as an opportunity to look for future collaborations, recruit future PhD researchers to our group, our postdocs, and also I'll be very happy to open um, the floor for future collaborations if we share the same um, research interests. So let me list a few projects here. The first is the smart wireless robot inline inspection for distributed pipeline network. You've seen some of the interesting results I presented in previous days, and I just want to give you under the NDE 4.0 framework. Then the second I will talk about an AI-enabled fiber optic sensor network sponsored by U.S. Navy, and AI-enabled NDE repair with robot learning sponsored by U.S. Department of Energy, and a field deployable miniaturized EM sensing system. And I actually spent time talking about this project sponsored by Con Edison. And the just some results on the wireless RF sensing and communication in hash environment, in which we are developing a completely battery-free passive sensing capabilities for hash environment. Of course, we would like to thank our sponsors for these above research projects. These are just some selective projects going on, and the more information you can go to our website or my personal website. I think our group website needs to be updated a little bit, but if you want to know more, feel free to email me, and my email is at the end of this slides. Okay. Well, this video just shows you the collaborative robot. There are two robotic arms in our lab, which we can do a robotic air-coupled UT for CFRP X-rays inspection. Right. So this is combining robotic and NDE for some complex shaped CFRP structures. And this is a real-time current array imaging for the corrosion on the paint problem we work with Department of Defense. Before we actually talk about projects, I want to preach a little bit more so we can understand the concept NDE 4.0 better. So I draw those building blocks here. Let's see if that makes sense to you. Remember, we have a complex NDE 4.0 framework, which I draw a couple of years back. But if you look at this differently, we'll start with a hardware layer where we have robotic solutions, we have multi-modal NDE SHM sensors, we do data acquisition and edge computing there, right? Then we can go to the second layer. This is a software level or software layer where we have the interface and models defined between the software and hardware. On top of this hardware layer, the software layer will do the data visualization, data registration. Basically, you just want to have a better data conditioning, storage, interfacing before you reach to the top layer, where we do a lot of algorithm development. So that's where we do the damage detection, categorization, material categorization, interpretation, and more importantly, based on that, we can do decision and control. Well, hardware layer, we do sensing where we need to understand the models. It can be physical models, it can be learning models, or it can be just simple, statistical models help you to understand the data. Well, you get data from the hardware layer, and now you can go to this software layer, where I call computation layer number 1. The next layer, you're going to achieve that through learning and inference. And for the second layer for computation, you do algorithms. As I mentioned, decision control is important. From that, the NDE 4.0, different from 3.0, is you are having this closed loop. And from the information you're getting from the top algorithm layer, you want to better control your hardware layer. So you can have a better way of doing data collection and computing there, facilitated by robot. And I want to take a step back of the definition of robot. Well, a crawler controlled by a human operator, strictly speaking, that's not a robot. A gantry doing a 2D or 3D scanning controlled by a computer, strictly speaking, that's not a robot. A robot should have both intelligence by itself plus the motion I just mentioned, right? So where does that intelligence come from? It comes from this closed loop. Well, this is the second view of ND 4.0. Well, let me try to brainwash you a little bit more. From my own terminology, I call this three-legged stool, like a stool, a chair with three legs. And what are those three legs? They are data, model, learning, and inference. Those are the three legs important, and they are the key components of ND 4.0. We start from the physical systems, right? We can use sensing. This is what you learn in course number 1, and also we learn in course number 2, how we can gather data from the sensing of the physical systems. Well, you can also do modeling. Modeling is nothing but a simple mathematical way of understanding the physical systems. So you can have models developed through modeling, and the data and model, they can all pass to learning, right? You can have data-driven approach, you can have model-based approach, and you are understand well the physical problems, the physical systems through learning models. And here we can just limit ourselves in AI models here. And to do a good learning, you basically are determining the parameters of those AI models. Well, models can also generate data, right? Well, you can also use data to estimate the model. That's something we can call likelihood, right? Well, for models and learning, you want to do inference. And all these things here will be your cyber systems. You do a lot of computations here in the cyber system. Well, for the three-leg stool model, we need to have data, we need to have model, we have the learning and inference. But I highlight uncertainties here. I'm a person who believe the uncertainties are important, need to be understood, but they are not yet being understood. They are not understood very well, as of now. So we need to look at that with uncertainties. So everything here being highlighted here is a cyber system, and together you have a cyber physical systems. Well, NDE in the cyber physical system framework is NDE 4.0. This is my definition at this stage. And let's look at this beyond NDE 4.0. From all those three legs, can I integrate them to have an integrated smart system? Is that NDE 5.0? Well, some researchers out there talking about 5.0 already. Well, if industry people talk to you about 5.0, maybe that's not, I don't think that's ready. Industry people still understand 4.0 right now. So academic people like to talk about new concepts, but I think this is a good time and the right time to talk about 5.0. So what is 5.0? We need to define that in advance. And one key element that I want to point out here is we need to have a good way of doing uncertainty quantification and understand uncertainties. And let me tell you why. Because we're going to dealing with a very complex system that the data need to be shared, and all different methods of NDE will generate different kind of data based on different physics. So each component will understand each other not on the data level because they are different. Then you understand that from an information level. But if you want to do that, you have to make sure you have a way to quantify the associated uncertainty for each component from data, from model, from learning. So each data can understand, each part can understand, each other on the same unified framework. Okay, so with that, I would like to show you some examples here. I will not, re-explain what I just, did before in previous days. So this is a project we were working on. We get AI involved to do the shared control between the human operator and the robot. And I explained this problem, big picture, very well. What we want to achieve there is first a smart and effective surveillance and inspection by understanding a new way of doing ND sensing, and also from a materials level, we want to do a better plastics failure modeling. The bidirectional and complex maneuver of the robotic system without impeding the flow will be achieved by a smart and adaptive robotic mechanism. Sorry, the optimize the damage assessment situational decision making will be achieved by the AI and the semantic reasoning, where you can have data-driven localization, mapping, fusion, prediction that combine both robotics and NDE together. This shows you one of the previous version. You've seen the video we did in 2019. This is a robot for large diameter pipe, 6 inch and above, where we developed this structuralized sensor and published in 2021. This shows you, you've seen this video before, and this shows you how we do the data communication to realize a wireless robotic platform. And also we can have onboard computing capabilities, data storage, and do the wireless data communication. So you can have high resolution data saved on board, while low resolution data can be transmitted. So help the operator to do a better real-time feedback control and decision making. This shows you the video of doing structured data collection and reconstruction at the same time. You can see the left is the sensor moving inside the pipe. You will see the vibration there, and also loss of the data. This is one of our early prototype. While the 3D reconstruct surface with high spatial resolution is shown here. You can see some of the defect signature being revealed. Right. Okay, so this is a video we made this year at the PRCI meeting. Let me play this to you. So this is a team we had at Michigan State and UMass. I don't know if you can hear the sound or the music. That's fine. You can just ignore it. So this is a new version of robot where everything is 3D printed. Operating at different orientation with this small diameter robot. So real-time data collection and processing when it's moving forward and backward. This shows you the reconstruction results, and we've done IMU-based data registration, which is not showing in this video, but I think that paper will came out very soon, and also answer qualification here. Okay. Well, we can revisit this Industry 4.0 and ND 4.0 framework I do previously. So I highlighted something in yellow and white here. The white is what has been achieved or accomplished in this robotic structured light inline inspection project. So we introduced new sensors there. We developed the edge computing decision framework. Through wireless communication, we do advanced data processing based on AI technologies. The snake robot has been integrated with NDE sensor. Well, those terms in yellow is the ongoing work. So we are expanding the sensing capabilities to other sensors, for example, eddy current array, ultrasonics, to integrate with the robot. With the data collected to leverage the cloud computing and big data technologies, and with information fusion from multiple sensors and also from other information we're retrieving from the data collection phase, will achieve the semantic learning and close this loop, right? So this is for this robotic structured light inline inspection project. This is another project sponsored by Navy, where we integrate fiber optic sensing with AI and data collection. Well, the key innovations here are two-folded. One is we are not just using fiber optic sensors to do the data collection or monitoring of the structural behavior. We are using AI to control the sensor network. In other words, we want to get the data from the sensor network, then from that, the AI will tell us, okay, which part of the structure we should look into further. In other words, we can fire those a couple of selective sensors in a smart way that we can use our limited resources more efficiently. So we'll have intelligent sensor actuation, and also the data will be processed using deep learning framework. So we have a better way of doing diagnosis and prognosis here. Another innovation here is done by one of our colleagues here at Michigan State, Professor Han, who is an expert of fiber optics and fiber optic sensor. And this is the omnidirectional fiber optic sensor. And you can see the size of this sensor comparing to the US penny, 1 cent coin here. And this picture show you that this is different from conventional FBG sensor, which is sensitive to only some directional information, but this can sense 360 degrees if you mount this on the structure. Well, I will skip this, just showing you the key tasks of this project to achieve smart sensor activation, actuation, and power management, real-time AI-enabled data storage analysis and damage diagnosis for SHM. Then we want to achieve low latency edge computing and statistical analysis capabilities for this project. Well, just show you some results. Since this is a data processing and inverse problem course, just select some results here. So from the measurement of the fiber optic sensor, you can understand the crack growth rate. In other words, you can tell, is the crack growing fast or at what rate is growing. You can look into the data in the time domain. You can also look at this data, in a statistical way or in the frequency domain, that you can predict the defect growth rate. And also, this is a new way of looking at this in frequency time domain, where you can finally reconstruct the damage growth over time. Well, all everything's collected by this novel sensor that you can get information from this omnidirectional sensor. You can get here it is actually acoustic emission sensor sensing from all directions when you mount this sensor on the structure. So the damage growth rate and AE source localization can be solved using this deep neural network learning framework. So we're doing some fundamental research here using plate geometry. Then hopefully this will be on more realistic naval structures. That show you, some intermediate results we have for edge for defect localization using one single fiber coin sensor, and also we can, estimate the crack growth length and rate using DNN. So for this project, you can also see the highlighted white, which has been accomplished here, and also the yellow one, which is ongoing effort. The third project is an interesting project where you see robot, NDE, and repairing in the same time. This work has been published last year on materials evaluation and funded by Department of Transportation. So the objective of this project is to develop an integrated autonomous robots that are equipped with a variety of NDE sensors to perform real-time inspection. Here, it's a specific problem. This is a power plant boiler furnace walls, which is very difficult to access. And due to the size of it, and also a lot of vertical walls, we have to develop a robot to climb on those walls and doing the real-time NDE. Well, not only doing the NDE, after we do the NDE or the robotic learning, we want to perform real-time on-site or live repair using the same device. And artificial intelligence here will help us do the smart data analysis and autonomy for both NDE repair as well as the robotics system control and decision making. So this just shows you, you've seen this idea here. We try to do multi-level, multi-modality data fusion here. So for this particular problem for the boiler inspection repairing, so we have to achieve three major tasks: 3D mapping, information fusion, spatial temporal crack tracking, and map updating, then do smart damage analysis by robot learning. So let me show you some results. This is the overall framework, combines NDE, reasoning, we have execution layer, damage analysis, and SLAM is for the robot. This picture shows you the final system. You can have NDE sensor at the front. You have another, optical sensor here. You have this is GIAN for the data computing on board. We have LiDAR sensor here, and also have repairing component at the end. So show you some results. This is before and after repairing. The orange signal here, which is the ND signal. The amplitude here corresponding to or proportional to the length of a defect. And after we do the live NDE, then do the live repairing using FSW, friction stirred welding technique to repair the surface crack, and then do a post repair assessment using NDE, and you can see those NDE signals in blue, which shows you a constant amplitude of the same site before NDE and after repair. We do another post repair NDE. So those are the two signals showing you the capability of this system. This is a project, I talk about sponsor von Anderson. I just want to show you some results here without going to too much details. And I just want to show you, this is a video. Let me play this. So this is X-ray CT data. Let me see. It's not playing well. Anyway, I don't know why this is not playing. Oh, okay, it's playing now. So this is X-ray CT data. We also have the crawler-based and the miniaturized system for the data collection and processing. And this shows you the physics model, experimental and simulation data comparison. Right, so this 3D model will help us to understand the damage features well. Right, so we do both hardware and software development, as well as data reconstruction in the 3D space. I'm gonna flash some of the results here. You have the slides. I share that with you. So I just want to point out a few key results here. We have done EM plus X-ray CT data fusion, where you get the 3D data from X-ray. You do data processing to fuse that with EM in the same data format. Then do data fusion, cross-validation there, and which will ultimately help us in the POD and the uncertainty quantification study. So some video on the high resolution and low resolution X-ray CT data. So the right is the high resolution data. The size for one pipe is over 100 gigabytes, and we can reduce the size of it to 150 megabytes while still preserve the damage information. So with this 10 to the order of 3 reduction in data size, then it's possible to reprocess the data and fuse with EM data. So this is how we do that. And we get a similar data format like what we're getting from the EM, the axial direction versus the circumferential direction. Then do data processing, get the information of the depth of the defect, the size and type of the defect. Then color code them into different layer information, coded defect, and also you can see the size of it. Let me show you some, correlation study. So you can see the X-ray and also EM data. You can have a very good correlation here, what you're seeing from both modalities. I think this also shows you actually process EM data versus X-ray, right? So these are very promising results. And by considering the X-ray, you need to have a industrial X-ray CT facility, and this is very difficult to get this deployed in the field by considering the constrained space we're dealing with for the underground buried pipes. While the miniaturized system from the EM system can give you very pleasant detection results from here, right? And also you see the power of image processing that you can highlight the location and the size of a defect. And in last lecture, it is not recorded due to the patent issue. But in that lecture, I show you some preliminary results using deep learning that can process the data and identify the defect locations while removing all those background noise. If you just look at intensity-based results, you will have a lot of false alarms here. Okay, the last example I want to talk about is the wireless IF sensing for ND and SHM. This is an application where you can see this used in the harsh environment, for example, in the nuclear power plant, for high radiation, high temperature, high pressure operation conditions. So how we can develop a wireless battery-free sensor and also do data communication using acoustic other than electromagnetic communication, because some of the structure there is attenuating the EM or even blocking the EM signals due to the size and also the materials. Right, so how we can do a better communication there using different energy, and also how we can use energy harvesting to make this into a completely battery-free sensor network. There are some ideas there. I believe those are in public domain, published by DOE technical reports, so you can get that online. And so this project is going to be very valuable for harsh environment monitoring and NDE problems, where you can deploy numerous sensing nodes installed around the facility. Well, if you look at this at the big picture, where I use the example of nuclear power plant facility here. You have the location where you're going to get the data collected. You have those data communicated, or those security communication platform, and interact with your offsite center where you do data analytics, decision making there. And this is a nice framework, but it can be easily extended or make some changes to apply to other applications. For example, in the aviation and aerospace, in the transportation, and so on. Right. So this is another ongoing research here at Michigan State. Well, before I conclude my today's talk, that I want to give you our version of ND 4.0 and Industry Internet of Things, or Industry 4.0, that the IIoT help to capture and leverage ND data. But we have to do a lot of work to advance the data engineering, data communications, and data computing. Well, IoT and ND, they can help to provide an intelligent, but not necessarily real time, right? You'll see a lot of applications, real time is not required. But as I said, intelligence is very important here. Okay. And you can do monitoring, you can do inspection, evaluation. And another important thing I want to convince you is you want to do intelligent control. Either intelligent control of a sensor network, intelligent control of your robotic solutions, intelligent control of your sensor and or edge computing. So you can make this really useful for manufacturing and operation process in the Industry 4.0 framework. Well, ND 4.0, what we're doing here, and you've seen the previous examples, it enable the next generation system health management. I replace the word structural here because it's not just a structural health monitoring problem. And there's research programs here, in the US, and I believe probably also in India and other countries, that SHM now stands for more on system health management instead of just structural level. And this can assure the optimized in-service maintenance on the IIoT infrastructure, right? So NDE is a key element of Industry 4.0. And the NDE 4.0, our vision is the cyber physical system framework, where you see what we are pioneering here in sensors, in communication, in computing, in data analysis, including data augmentation, data processing, of course, including inversion here, right? Plus the control through the learning and understanding what we're doing here at each aspect of it, which are data, models, and learning. Well, let's revisit this again. So we are now in the Industry 4.0, NDE 4.0 here. Well, today, I believe we are on, on the, onset of Industry 5.0. It might be early for industry to adopt 5.0 concepts, which I think that's perfectly fine. But for researchers, I think this is a good time for us to think beyond 4.0. So the new paradigms in NDE means that we want to think about intelligent action and control, better decision making through new ways of data collection and outstanding quantification of those data we collected, and real-time assessment and action taken. Well, if you look at the complexity versus the time here, well, the complexity definitely is becoming higher and higher, right? But just look at this trajectory and believe because of the higher complexity here, which means there are larger opportunity when we're moving from 3.0 to 4.0, 5.0. Well, some trends here. I use the slides from Professor Udpa's presentation. I think she prepared this, and I totally agree with that. So there are a lot of enabling technologies we're doing now, including AI, blockchain, virtual reality, augmented reality, mixed reality, additive manufacturing, communications when talking about 5G, 6G, quantum computing. And we try to reach some of the goals that we are envisioning here, like mass personalization, increased productivity and consumer experience, then bring back human in the loop for the 5.0 concept. And there will be collaborative robots there, or co-op robots, cobots there, right? this is the future trends for 5.0. Well, what we can do for NDE people, I list a few things here, and I believe there are going to be a lot of research opportunities out there when we talk about those items. The last slide is borrowed from internet. This does not represent my opinion on Industry 6.0, okay, or the sixth industrial revolution. But I definitely appreciate that this is a bio-based industrial revolution to achieve the goal of intelligent society. So you can look at the sixth wave or the sixth industrial revolution here in terms of the bio-based concept that you want to achieve a more sustainable, more bioeconomic, renewable energy centered society. And I think this is the future of our society. And another thing that is because, Michigan State, we have our, how to say that, we always say go green, right? Go green, go white. So I think with that, I think our society should go green when we looking at the future ahead of us. So with that, I will stop here. I think I plan to use 1 hour 30 minutes to deliver my last lecture for this GAN course at VNIT. And before I open for discussion and take questions, I would like to thank the organizer for giving me this opportunity to deliver this lecture here at the VNIT and also on the internet, and also give my thanks to Professor Rao as the course coordinator, which we spent a lot of time on communicating, and thanks for helping me and Professor Lalita Udpa to prepare for these two courses and deliver here to the students. So with that, thank you again, and I'll be very happy to take questions. And after Q&A, I am hoping to use the last 30 minutes with everyone here in the audience, also on the internet, to have an open, I'll say open discussion is also an open-end discussion, because a lot of things that I don't understand very well, and I hope that discussion can help us to spark some new ideas to look forward. With that, thank you again. So I'll stop here. Any questions from the audience and the internet, I'll be very happy to answer. Thank you.
Hello.
Yes.
Yeah. Thanks for your support too. I'll just check for
My
the
pleasure.
questions. Any questions from the audience?
Okay.
Hi.
Hi.
Yeah, and 5.0 NDE, shall we expect hybrid NDE technique, like it consisting of eddy current sensors and ultrasound sensors and microwave sensors included in one equipment, and it will useful for any type of materials?
Okay. This is a question asking for we call the silver bullet, right? A silver bullet means that you can have something that do it all for you. Well, the idea of having a hybrid system is not new. You already seen system out there which can have hybrid NDE methods. Well, in medical or medicine area, you'll see like PET CT, PET MRI, and so on, that you can get both, for example, functional and anatomical information. For ND, it's the same. We actually doing that, but not. I don't think we have a system that doing it all, combining all the physics together. Well, the reason we don't see that nowadays, although I believe in terms of the maturity of the technology, it might not be that hard to do it, but we really has not identified a problem that we really need to get all those data at the same time. But I think, you know, that depends on how we understand how we want to solve the problem. You know, you know, we do see some materials that we hope to get both EM and ultrasonics information together. But still, for ultrasonics and for EM, there are different methods out there, right? For EM and different frequencies there. So yeah, hybrid definitely. I believe that's right way to do it. Instead of using hybrid system, we can also have a term people use a lot called multimodality, right? Multimodality, you can have multiple data, do the data fusion, information fusion, but not necessarily have one physical system do everything for you. You can have multiple systems collect the data for the same problem. You just do the data registration and do that. Well, I think this is something that we're doing here now in ND 3.0 and 4.0. For 5.0, maybe we'll have some new problems, we'll have new challenges, so we can have some silver bullet there. I don't have a, you know, the answer for that yet. Now, hopefully I answer the question.
Thank you. In 5.4, shall we expect in mobile ND techniques?
Can you define your mobile for me? What do you mean your mobility or
Mobile
mobile
means
ND?
we have a mobile phone. Every person has mobile phone. So mobile phone as a ND equipment.
Okay. Some people in the industry may not like what we're gonna discuss here. You know, we do have some project. You can see that, you know, some senior students they convert a mobile phone to an ND device, right? They can have a mobile phone to do like any current measurement or for some particular frequency range. You know, with the mobile phone we have nowadays, it does have the capabilities of doing the computing we want to do most of ND in terms of data acquisition, data processing, and so on. If we can expand the mobile phone to a useful ND device or tool, I do see that's possible. That's definitely possible. And I believe this is my personal opinion, right? It does not represent for any industry, and I believe you know, more mobile NDE or like more like a crowd funding type of mechanism of crowd data collection. Everybody can contribute. I think that's the future. But one concern, or maybe several concerns there. One is how you can make sure the data is being, you know, it's a secure. The data is actually being validated. Who's gonna check that, right? And with everybody sharing that data using mobile devices, how we can actually better understand those data, that's something still not clear to me. Another thing is, as I said, the industry may not like that because ND is a very specialized field. That's my personal opinion, right? That's why people need to get certified. People need to get training so they can actually work on some ND problems. It's different from measuring your blood pressure and pass everything, send all the data together to do some API data processing and so on. ND is a specialized field, and but I think it's moving forward, but probably moving forward slowly and more importantly carefully. So we're gonna, we always say do it slowly, but do it right. I think that's a philosophy we should do if we want to move this into what you just mentioned, mobile NDE type of concept.
Yeah. So for as a ND engineer, for image processing, the person is required advanced image processing or basic image processing techniques are enough.
Well, I think basic image processing, definitely required, but not enough. That's what I'm very sure based on experiences, right? Basic image processing, if you look at an image processing textbook, let's say the widely used Gonzalez textbook, right? That's what we use for undergraduate and graduate level image processing, and a lot of signal processing book out there. But you see, this is something related to NDE education, and you see some country has bachelor degree for NDE. US, we don't have a bachelor degree for NDE. Well, we have the NDE training at a graduate level. And at a graduate level, we expect them to understand the basics in signal processing and image processing, while they need to get trained to understand the physics of NDE. So then the image processing, data processing becomes more meaningful when you're dealing with NDE problems, right? Just like the data we are getting, for example, you want to do signal processing of NDE, some particular NDE methods. Let's say you want to do filtering in the frequency domain, but you need to understand the physics of it so you can apply either band pass filtering or notch filtering or band reject filtering and so on, right? So that's something that you have to learn at graduate level if we don't have a bachelor level education here. So go back to your question. I think definitely we need advanced training. That's the reality in the US that we don't have a more like a bachelor level, general level of engineering training here. I'm not sure about India. Maybe you can educate me on that. So what you guys are doing there. Another part is, the technician training, right? You don't have to even go to the college to do ND inspection, certification or training. But that part of training that usually don't go too deep into the math and physics. So we engineers, I believe, I know VNIT is a premier engineering school, and for engineers, we need to understand math and physics very well. And engineering for NDE is definitely advanced to that. So that's my personal opinion for it.
Yeah, I have a. Can I know what kind of advanced systems are using in um, Michigan State University, like in the configuration of the system, computer?
You're talking. Are you asking about the computing
Yes, yes, RAM and
facilities?
the computer RAM, random access memory, and
I see. What I definitely don't have all the numbers, but I know where to direct you to. You can go to you can search HPCC Michigan State, and they may have a different name now. We have high performance computing facilities. There's actually a department doing high performance computing, and that's the resources shared by all the researchers at Michigan State. Well, the College of Engineering, we also have our own high performance computing clusters. It has changed over many years. When I was a graduate student, probably like 15 years ago, we already have high performance computing clusters with a lot of RAMs and um, computing cores and so on. So if you want to have the information, you can get it from online. There's a department doing that. For NDE, we definitely benefit from that. We submit our job there, so we can do a lot of computational intensive type of job there. But I'm sorry, I don't have the numbers for you, but
yeah,
it's online. Yes.
okay. And I'm very happy to listen your lectures. And I have learned a lot of techniques and how to work on each technique and how to approach this each techniques. So I got much knowledge from these lectures. Thank you.
Very
Thank
good.
you very much.
Yeah. I appreciate your feedback, and I'm very glad I can share this with you. I know this is like a 5-day very intensive course, and I appreciate the students are with me. I cannot see everybody's faces, but I hope that everybody's are with me, and with this intensive course, I suggest think or learn beyond this course. I think that's the purpose of having a course like this. It's not just to get everything understood or learned through 5 days or 10 days, but open some doors for you to think, to collaborate. And yeah, that's why we are here. And that's why you are here, right? So yeah, but thank you so much for your feedback.
Yeah, thank you.
Thanks.
Okay, we have one more question. Just
Okay.
what is the current scenario in microwave entity in industries, and what will be the future scope in this field?
Okay. Okay, I'll try to answer this question, and I'm sure there's quite a few people out there in the microwave NDE are more qualified to answer this question for you. But let me try to answer based on my experience. So for microwave NDE, I think it has been there for many years. If you look at the recent review articles on microwave NDE and millimeter wave NDE, I think there are several directions I think this can definitely go to. One is how we can make microwave NDE more user-friendly and easy to operate. Make them into a more industry or field-ready technology. I think that's one direction that you definitely should look into if you want to make this more useful in the industry. Comparing to other technologies out there, microwave is still relatively new, right? Although it has been in research for many years, but look at the industry now are adopting or being widely used there, eddy current magnetic particles, right? Dye penetrant and ultrasonics. And well, microwave is also a technology I believe that's been certified and you can have certificates from that, which means people are gaining more traction, so adopting this in the industry. So besides making this more friendly, in terms of system, in terms of data interpretation, there are other things I think what we can do is more on the microwave devices. Okay, and I want to mention this not only for microwave devices but also for example for terahertz, and I believe those are some technologies that are facing the same challenges but also opportunities for the industry. So you'll see a lot of advances there in terms of the devices research and development there. You see those portable systems out there. So that's something that I think definitely industry is seeing the potential of it. Since I believe it's always in the data processing and image fusion. Now, my personal experience, from microwave, a lot of work has been done on this frequency range, right, from 300 megahertz to 30 gigahertz. But you'll see there are tons of applications out there where people are trying to explore the microwave's potential at different frequency bands for different applications. So I believe if look at this from the application ends, that probably will spark a lot of new ideas. For NDE, I think microwave, you've seen a lot of interesting applications. For medical, you also see microwave. But we talk about microwave, for example, for breast imaging, there's tons of papers out there. There's a lot of NIH funding going to that area. And I really admire a few people in this area for medical applications. But somehow there's some bottlenecks. You can read that more. I don't want to mention this today online with everything being recorded, but I hope that you can read a little bit more out there. And I think this is a promising field, but with several bottlenecks that we need to address. That NDT is also going to see the same, which I'll be very happy to discuss with you offline, and I'm also happy to direct you to some reading materials. But this is what can I share with you for this field. Hopefully you are happy with my answer. Yes, of course. Yeah, I'll be very happy to collaborate with any of you on new microwave NDE problem. We are doing microwave a lot at Michigan State. And if you are interested in that, definitely, sure. Yeah, looking forward to it.
Let me check. Any other questions from audience? The online one.
Yeah. Besides question, I remember yesterday I said, I want to also hear from you. I think the first student, I really appreciate your feedback. Sorry I didn't get your name. Maybe I'll ask Professor Rao later. I now know you as a microwave guy, but I was really impressed. Now also impressed by the questions throughout this course. If you have anything, any ideas, anything that you want to share, I think this is a great platform for us to discuss, and I want to learn from you as well. I'm sorry.
any other questions or any discussions that we would like to have from the audience?
Okay. If no more questions or discussion, my email is here. Anytime you can send me email, or you can talk to the coordinator, Professor Rao. So we can definitely talk more offline. As I said, this GIAN course is a great opportunity for me to get connected with the researchers at your institution, and it's a great honor for me to know you more, and I look forward to collaborate and know you better in the future.
Okay. I don't think any. Okay. So thanks a lot, Dr. Aiming. And along with you, I would also like to thank Madam also that you both agreed for delivering the lectures or the course. And you can say we were fortunate to get both the courses approved from the GIAN portal too. And I understand that these two courses were quite hectic. That means the course content was quite large. It was not that easy. And though entity includes a lot of domains, it's not specifically that you know only one type of analysis or only one method works here. You need a lot of knowledge about electromagnetics. You need a knowledge about you can say signal processing, image processing, systems, everything you need. So the course is already hectic. So thanks a lot for your help and support. And so I think then we'll wind up here. And in afternoon session, we'll have a lab. So the submissions will be open for all the students, and I'll be conducting the lab. So in case any, if you have any issues regarding MATLAB or anything, like you can drop me an email, or the session will be open for, you can say, submission of your assignments.
Yeah.
Yeah.
Yeah. Thank you so much, Professor Rao. It is my honor, as I said, and thanks to everyone who joined this course. And without the student body, without the interaction, this course is not complete and not possible. Thank you so much. And I hope to visit VN19 in person next time. Sorry, I cannot be there this time. I know, I did Google the city online, and I saw some campus tour on YouTube, YouTube video. So I hope I can visit you guys in the near future.
Yeah, I think I'll get a good feedback from ma'am too. That how was the campus and all in physical.
Yes.
Yeah. So yeah, thanks a lot once again.
Yeah.
So
Okay.
Yeah,
Yeah, we'll
so
be
we'll
in
wind up
touch.
now.
Yeah.
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 Thank you.
Thank you so much. Yeah. Bye bye.